This is section 3.10 on linear approximations and differentials. All right, so we're almost done with chapter 3. Homework is 1 to 33 odd, so let me go ahead and give that to you. So, topic on page 251, linear approximations and differentials. Okay, now, they give you formulas on page 252, box 1 and box 2. You don't really need them, in my opinion. They make a big deal out of L of x, the linearization. It's basically the equation of a tangent line to the curve, which we've done before, only write it as a function, make it look like y equals mx plus b. Okay, so it's called the linearization, linear approximation of the function at a given point. Okay, it's no different than the equation of the tangent line at a given point, just write it as a function, write it as y equals mx plus b. Okay. Then differentials on page 254 for differentials. Box 3, dy equals f prime of x dx. It almost looks like the Leibniz notation dy dx equals f prime of x, and then multiply both sides by dx, so it looks like this. A dy is called a differential, it's a tiny change in y. Dx is a tiny change in x. Okay, so there's not really that much difference between dy and delta y, dx and delta x, except dy is theoretically very small, and dx is also very small. Okay, so differential dy is just a derivative times dx. One way to think of it is dy dx, Leibniz notation, is the same as f prime of x, and then multiply both sides by dx. And then it kind of looks like that. Okay. Right, so let's see, we have 1 to 33 odd, so it's on page 256. Let me get those for you right here. So, yeah, it's up to 13, 15, 17, 19. They use linear approximations to give the following. Okay. 29, 31, and then 33 is over here. Okay. We're ready. All right, so linearization of a function, it's the equation of the tangent line written as a function, L of x equals mx plus b. So before we did y minus y1 equals m times x minus x1, and we may have stopped. Now you keep going, solve for y. So for example, L of x is negative 3x plus 10. So we just use L of x as an approximation, the linearization as an approximation to the function. Why would we want to do that? Well, we like straight lines. Linear functions are much easier to deal with than whatever the function happens to be. Okay. All right, so number 3, f of x equals square root of x, which is the same as x to the half, at a equals 4. A is a particular x value. So a square root function looks like this. So we're coming up with the equation of the tangent to the curve. Okay, so if I plug in 4, I get 2. So I'm at the point 4, comma 2. All right, so first I do the usual find the equation of the tangent to the curve. So f prime of x, derivative of x to the 1/2 is 1/2 x at negative 1/2, or 1 over 2 radical x. Plug in 4, 1 over 2 radical 4, 1 over 2 times 2, 1/4. All right, so the equation to the tangent of the curve is y minus y1, y minus 2 equals m 1/4 times x minus 4. Before we may have just said stop, but now we'll just keep going. Y minus 2 equals 1/4 x minus 1. Add 2 to both sides. So y equals L of x, my linear approximation, is 1/4 x plus 1. Okay, so in other words, for values of x that are very close to 4, instead of using this function, I could replace it with this function. Okay, and it'll do a pretty good job for values that are near 4. Here's 5, f of x equals square root of 1 minus x, and the point is 0, 1. Okay, so f prime of x is 1/2, 1 minus x at negative 1/2 times negative 1 by the chain rule. So that's negative 1 over 2 radical 1 minus x. Plug in 0, negative 1 over 2. Point, slope. So y minus y1 equals m times x minus x1. Solve for y, so y equals L of x is negative 1/2 x plus 1. Okay, now they say use this linear approximation to come up with certain values. So for instance, you say square root of 0.9. Okay, square root of 0.9 is the square root of 1 minus 0.1. If you look over here how the function works. And the square root of 0.99 is the square root of 1 minus 0.01. Okay, so they want you to use L of 0.1 in the first instance, because if I plug in 0.1, I'm taking the square root of 0.9. Okay, so by using the linearization, which is much easier than doing the square root function, most of us can't do weird square roots directly, but this is pretty easy to do. Negative 1/2 times 0.1 plus 1, 0.95. So in other words, my guess for the square root of 0.9 is about 0.95. And then L of 0.01, which would be my approximation to 1 minus 0.01 is 0.99. I'm roughly estimating the square root of 0.99. It's negative 1/2 times 0.01 plus 1, 0.995. Okay, so the problem's finished. Here are the actual values. Square root of 0.9, you can punch it in your calculator, 0.9487, pretty close. And on a calculator, square root of 0.99 is about 0.99499, very close to 0.995. Okay, so of course, the closer you get to plugging in, 0, then the better the approximation would be. All right. 11a just asks for the differential. Y equals x e to the negative 4x. The differential dy is just the derivative of this times dx. So this is a product rule. First times derivative of the second. Derivative of e to the negative 4x is e to the negative 4x times negative 4. Plus the second function, e to the negative 4x, times the derivative of the first, but that's just 1. And a little bit of touch up. So dy is negative 4x e to the negative 4x plus e to the negative 4x dx. Okay, so 13b, y is 1 minus v squared over 1 plus v squared. dy is the derivative of this times dv. So quotient rule, bottom times derivative of the top, negative 2v, minus the top times derivative of the bottom, 2v, all over 1 plus v squared squared. Clean up the top, negative 2v minus 2v cubed minus 2v plus v cubed. 2v cubed, they cancel out. So dy is negative 4v over 1 plus v squared squared dv. Okay, 17, find dy with this information and the given value of dx, which is like delta x. Okay, so y is equal to this stuff. dy is 1/2, remember raising something to the 1/2 means square root. So 1/2 3 plus x squared to the negative 1/2 times 2x by the chain root. 2's cancel out, clean that up, x over radical 3 plus x squared dx. Okay, so in this particular case, I plug in. So I plug in x is 1, dx is negative 0.1. So 1 goes here, 1 goes here. 1 over the square root of 3 plus 1 squared times negative 0.1, which is, that's 1 over 2, square root of 4 is 2, 1/2 of negative 0.1, which is negative 0.05. Okay, what does it mean? If I'm at x equals 1, if I decrease x by 0.1, I will decrease y by roughly negative 0.05. Okay. Okay, this one, f of x equals natural log of 1 plus x. I'm at the origin. Okay, so y prime is 1 over 1 plus x. Plug in 0, y prime of 0 is 1. So y minus 0 equals 1 times x minus 0, or y equals f of x is the linearization of x is just x. So if you want a good approximation of the natural log of 1 plus x near the origin, just use y equals x. Interesting statement. Okay, 19. Y equals x squared minus 4x at x equals 3. Delta x is 0.5. Okay, they want us to compare dy and delta y. dy is usually easier to compute. So dy is 2x minus 4 dx. Plug in 3 right there, 0.5 there. So dy is 2 times 3 minus 4 times 0.5. That comes out to be 1. Okay, what is delta y? If I plug in 3, I get negative 3. If delta x is 0.5, the new x value is 3.5. So plug in 3.5. 3.5 squared minus 4 times 3.5 is negative 1.75. So delta y, which doesn't involve calculus, is just y2 minus y1. So it's negative 1.75 minus a negative 3. which is 1.25. This is a lot more work though than finding dy. So it's close, 1 versus 1.25. There we go. Okay, 23. Approximate 1.999 to the fourth power. Okay, not by punching in the calculator, that's very difficult, but by using the linearization. Okay, so the function is raising to the fourth power, f of x is x to the fourth, and the nearby nice value is a equals 2. Okay, so we're at the point 2 comma 16. All right, so f prime of x is 4x cubed, plug in 2. 4 times 2 cubed is 32. So that's my slope. Y minus 16 equals 32 times x minus 2. Clean it up, add 16 and distribute. So L of x, the linearization is 32x minus 64 plus 16, 32x minus 48. Okay. What that means is that a good approximation for 1.999 to the fourth power, rather than punching it in a calculator, is just punch it into here, straight line. 32 times 1.999 minus 48, and it comes out to be 15.968. Okay, and then if you use your calculator, the actual value is 15.9. That's a 9. 968,024. So it's correct to 1, 2, 3, 4, 5 digits, and they don't, actually 6 digits, the 0 even matches. So not until you get to the 7th digit of the 2 are they different. Okay, 29, show that the secant of 0.08 is approximately 1. Okay, so f of x is secant x, the nice nearby value is 0. And the point is 0, 1. Secant of 0 is 1. So f prime, derivative of secant is secant x tangent x. Plug in 0, secant 0, tangent 0. Secant 0 is 1, tangent of 0 is 0. 1 times 0 is 0. So the slope is 0. So y minus y1 equals m0 times x minus 0. Well, that's basically just y equals 1. So therefore, secant of 0.08 is approximately equal to 1. That's a good approximation that we have here. Okay, 31, show that 1 over 9.98 is approximately 0.10002. So the function is the reciprocal function, f of x equals 1 over x, and we are near 10, a equals 10. Okay, so the function is 1 over x, x at negative 1. The derivative is negative x at negative 2, or negative 1 over x squared. The ordered pair is 10 comma 1/10, or 0.1. Okay, f prime of 10 is negative 1 over 10 squared, or negative 0.01. That's my slope. Okay, so y minus y1 equals m times x minus x1. Okay, or y equals L of x is negative 0.1x. Okay, and then we have plus 0.1 plus another 0.1 or plus 0.2. Right, now, if I want a good approximation to this, I'll just plug in 9.98. So negative 0.01 times 9.98 plus 0.2 comes out to be 0.1002, which is what was asked for in the problem originally. Okay. Then 33. Last one here is a word problem. The edge of a cube was found to be 30 centimeters with a possible error of plus or minus 0.1 centimeters. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume of the cube and the surface area of the cube. Okay, so volume is x cubed. dv is 3x squared dx. Area, well, there are 6 faces. Each area is x squared, so 6x squared. So dA is 12x dx. All right, so the maximum possible error in dimension is 0.1. So that's my dx. So dv is 3 times 30 squared times the dx at 0.1. That comes to be 2,700 times 0.1, 270 centimeters cubed. dA is 12x dx. So 12 times 30 times 0.1, 36 centimeters squared is the possible dA. Okay, then they ask you these other things. The volume is 30 cubed, which is 27,000 cubic centimeters. The percent change in V is 270 over 27,000. That's 100, 1 over 100, or 1%. Okay, so the relative error is 1 over 100%, error is 1%. So by changing x by at most 0.1, the greatest possible error in volume is 1%. That's what that means. For the area, 6 times x squared, 6 times 30 squared is 5,400 centimeters squared. Possible percent change in area is 36 divided by 5,400. That's 2/3%. So the maximum possible relative error is 1 over 150. And the percent error, greatest possible percent error in the surface area is 2/3%. All right, so this is section 3.10.